Okay. Good. Okay. See. Excellent. Excellent. Hello, for people who are joining in this moment. Just making sure all the streams are live. Oh, I got audio. Let's turn that off. Okay. Okay, we're gonna go ahead, go live on LinkedIn. But thanks for joining us on YouTube and Twitch. This is fun. Come on, LinkedIn. Go. LinkedIn is being very slow at the moment. Okay, give this another 2 minutes, I guess, and then I'll try to restart it. Okay, come on, LinkedIn. Hello, welcome to the YouTube and Twitch stream. Hopefully we can get the other stream up and running. Okay, go live. Okay. I guess we'll just share the links. Okay, let me go grab the links real quick. Okay, good shareable link. Okay, we're gonna have to move forward. I'm sorry for those who are waiting on LinkedIn, but it is not going live. It's just sitting there thinking. Okay, so thank you for joining us. I'll keep eyes on LinkedIn and see if that works. Well, let's go ahead and get into the content. It's been about a few minutes trying to get this up and running. So, welcome to this live stream. We're going to be going through the Altera FPGA AI tools. Specifically, we're going to be looking at how to go from a PyTorch model to get the data, to train it, to generate the model, and then export that to OpenVINO and the DLA compiler so that you can run it on the FPGA device. I'm FPGA Zealot, professional also Andrew Wilson. You can find me on YouTube, Twitch, LinkedIn, Twitter, whatnot, Twitter. Just a few disclaimers as we get started. This is a sponsored live stream sponsored by Altera, which is, I'm grateful for this opportunity. I am not employed by Altera. I do not offer support as like a FAE or field application engineer or anything like that. The content on this channel is for information purposes only, and it's my opinion. So I would like to get started by going through the MNIST example that is over here. So I'm going to put this link into the various chats so you guys can follow along. Grab the link. So feel free to follow along with this link. We're gonna go ahead and walk through the example that we have today. So for this example, you can either open it in Colab, or you can open it locally and be able to go through the PyTorch example together. I'm going to go ahead and do run all on both of these. And if you are running it locally, you may need to change the number of workers in the data loaders to 0 if you see like a lambda error come up. But besides that, you should be able to run it on Google Colab or be able to run it locally. So today we're going to go over MNIST, which is one of the most kind of basic examples for a convolutional neural network. Feel free to, as we go through and talk about this neural network, feel free to say hi in the chat, tell us where you're from, your interest in FPGA and AI, and your experience with neural networks. Okay. So this is a really cool public example of what MNIST does. So MNIST is a handwriting classification tool. And for the example we're looking at, it's classifying 0 to 9 in kind of a handwritten fashion. So if we write 0, it goes through these different convolutional layers, doing downsampling, more convolutional layers, and then going through back to the fully connected layers here to the final output where it gives you a value, a max value between 0 and 9 of the indices. And feel free to interact with this to understand what's going along. It's supposed to be a 9. There we go, a 9. Now we do The 4s seem interesting, like being close to a 7. Get to 9. Let's see. How do we write our 7? That. I still think it's a 9. So it's not a perfect system, but you can see how the layers are interacting. So we want to be able to build this from scratch and to train this with PyTorch. And we're going to be building off of the example that's in the top link here. If you want to kind of follow around where I got all these commands and whatnot, you can run through this example, which is basically pulling in the same information. There's a lot more detail here and explaining the process and how the system works. I kind of pulled out the critical information so we can go ahead and work through the example quickly. You're asking for the library? Okay, no, you found it. That's good. So, after setting up PyTorch correctly, we need to load the data, and luckily, it's very easy to load the training data and validation data for MNIST using these commands. One important thing that we're going to do here is we have a special lambda. This is for converting our grayscale image into a 3-channel image. And this is mostly because the FPGA example we're using has a video DMA core that it's using to stream data to our AI IP. So we need to be able to have 3 channels to match kind of the expectations of the hardware. If we had more time, we could probably go into the hardware and modify it in such a way that it could be able to take the grayscale just fine. But in this situation, we want to just kind of match the expectations of the hardware, and we'll talk about how this affects the model. So we're going to basically create 3-channel grayscale, and then we can load our various handwritten symbols. And these handwrittens, we're going to have 3 channels, and they're going to be 28 by 28 pixels. Kenan, yeah, hopefully we're not going to dig too down into the exact details of like PyTorch or neural networks. We're just going through a basic model. You should be able to run these fairly easily to generate that model if you want to, and then follow along with more of the FPGA specific details for taking that neural network and compiling it down to the Altera FPGA design. So once we have collected the data, we then need to build our model. And like you saw earlier in our visualization, we have a convolutional layer, like the max pool downsampling layer, another convolutional layer, max pool downsampling, and 2 fully connected. So that's what we're going to do here. We're going to do the convolutional, like that's the activation, and then the max pool to downsample. And we have 2 layers of this, and then we have 2 fully connected layers. And this builds our very basic convolutional neural network. And then once we load it, we're going to train it. This, if you read the other thing, they'll go into more details of what they're doing to train, what type of laws, what type of training they're doing. In this situation, we're going to do 15 epochs, so it's like 15 training cycles of this specific model and the training data we loaded. And it will run the training data for 1 epoch, and then it will validate it. And we're going to do this for 15 epochs. Oh, this is going to run for a bit. To improve the speed, you can change the runtime to a T4 GPU. I probably should have done that to begin with. But we can just keep walking forward with the example and then go back to when it's finished training. Actually, this might be faster. Let's just stop this real quick. We're just going to jump into change the runtime to the GPU. Gonna take a few seconds to get up and running. And then we're just going to run all. Okay, so that's going to reload and train using the GPU on the Google Colab instance. Okay. Well, thank you for joining. Why this is training, we can do maybe some more a little bit chatting. I meant to this be a very easy to use example for doing a custom neural network and then showing how we transfer it to the FPGA. So hopefully it doesn't take too long to retrain the system. But once the system is trained, we'll be able to use OpenVINO using the version supported by the FPGA AI tools, and then export that as a XML file that we then can implement onto the FPGA design. We have a question from YouTube chat. What is doing the training, a server or your local PC? So in this situation, on the, let's go scroll down here. So on the left, we have a server. This is a Google GPU server that is training on the left. On the right, I am running it locally using my own CPU cores. It looks like I did multi-threading, like a multi-threading of 8 across the CPUs to get this done in 5 minutes. I guess we could show this example, but it's basically the same. We're just exporting the model to get it up and running. Okay. Thank you for the questions in chat. So now, once we have the model, we can then open up our FPGA AI tools. So this is using the Windows subsystem Linux. We have the FPGA AI tools installed. And we can then, from here, compile the model to be used on the FPGA. It's gonna take a minute. So we'll do that in probably about 3 or 4 minutes. But while we're waiting, I just want to say if there's any new viewers that thank you for joining us. I am FPGA Zealot, and this is a sponsored Altera stream. We are currently looking at doing the very basic MNIST neural network on the FPGA, building it and training it with PyTorch. And we're currently training it. It should be done soon, and we'll export this to our FPGA AI tools. And throughout the entire show or live stream, feel free to ask questions. If you're watching this as a VOD, feel free to put in comments or questions, and I'll try to get back to you in a timely fashion. You can also join our Discord, the FPGA Zealot Discord, to be able to ask questions more directly. Okay, so that's not going to take too long. We can use kind of this pre-built example here to go through what happens in the system. So we're going to go up here real quick. Let me see. Can we? I guess we can zoom in that way. Okay. So we're going to make a directory and we'll call it stream. We're gonna go into stream. We're gonna copy over these here. Okay. Okay. So we have our two files, MNIST 3x binary and the XML file that are required and are generated by the OpenVINO export function. So now we're going to run the commands. So if we scroll to the bottom of our tool, we have a compiler command here. And this is going to take our MNIST XML. It's going to apply it to our architecture for FPGA and going to generate the bin file that we are going to copy over to the FPGA. I'm not sure if you paid attention to our frames per second on our previous videos, but it's usually like, around 100 to 200 to 500 frames per second. The MNIST is a much smaller neural network with a lot less coefficients, or weights, or how you refer to them. And supposedly, if we're running at a full 500 megahertz, we could potentially get up to 18,000 frames per second on this. While that is really cool, it may not be necessary for our target application. So in this situation, go here. We're using, scroll down, put that right there. We're using the Agilex 7 performance architecture for the FPGA. This is an example architecture. If we want to know the utilization, we can use the DLA compiler to tell us. This is about 62,000 ALMs and the various registers and DSPs and M20K memories. This takes about 10% of the Agilex 7 dev board I am using. There's other options. Is it? I think it's max performance. Let me look at that directory real quick. I'm going to do AG7. Okay, what am I looking for? I am looking for Performance Giant. There's Performance Giant. This is not spelling. Is that not? Okay. This one, so we have performance of 62,000 ALMs, and then we have Performance Giant with 62,000 and 116,000, so 116K worth of LMs, almost twice the size. So the bin file, so we have Tanner asking what the bin files are. So we have two bin files in this situation. I'll get to Tanner's question. We have the bin file from OpenVINO. I assume I can't just, let's see, if we just, probably not going to be, yeah, so this is just a hex dump. Let's see, do we have hex dump? I don't want to dump the whole thing. But it's a binary file. I assume it's a compressed file of the coefficients. And the same thing with the binary that we export. It's going to have the coefficients. It's going to have the layers and the functions kind of in a compressed format for it to be exported to the FPGA AI tools. And then we're going to explore two more other basic architectures. We have the generic architecture with 34, and then we have the small softmax, right? Which is down to 18,000. So we kind of have 4 different sizes, each kind of 2x bigger than each other. Tanner, you said mean the weights and feed-forward network and etc. Yes, that's the type of information. The weights in the feed-forward network are what's stored in the binary files. Okay. The training is done, right? We trained for 6 minutes and we exported the file. So if you trained the network on Google Colab, you can download the OpenVINO binaries and XMLs to be able to follow along in your FPGA AI tools. Okay. Make sure we get back where we want to move forward from here. So we first compiled the MNIST using the performance architecture. Let's go ahead and try the giant architecture and the small architecture. So we had about 16,000 in the performance, but when we did the performance giant, our performance actually went down a little bit. So even though your AI core is using more utilization, its configuration may not be optimal for your neural network. So it's going to be good to play around with the different architectures and figure out what's best. Because if we go to generic real quick, that's kind of interesting. The generic is actually much faster than the performance and performance giant architectures. And this is probably due to potential pipelining and the cycles between these different performance units. The generic is going to be more compressed and probably better pipelining to be able to perform a smaller network much faster, but may lack the the coefficient, the convolutional size to handle a much larger network. And then finally, we can do the small one. Even the smaller one. Well, I did break this up in 2 graphs, so you have to do like the collection of both of them. Okay. Not sure how much I trust it in this situation. So those are the different default architectures. We're going to go look at the dot file real quick to see what the graph of these neural networks look like. And then we're going to try to do a custom architecture to optimize what the FPGA hardware would be doing. Okay, so we're going to bring up the graph. So we're going to go to the stream folder here. And I think this is the one. Okay, that's 128. Those are subgraphs. Okay, let's try this subgraph. That looks like. Okay. So going back to our layers that we saw in the PyTorch, close this. We'll look at our model right here. We have the slice. Yes. Okay. There we go. So I'll just drag that over like that a little quick. So this channel 1 extractor is acting as a slice function right here. And then we have our convolution going into our ReLU to our max pool. So we got these right here. Those are the 3 modules that are happening within our FPGA right here. FPGA, FPGA, FPGA. And then our second layer of convolutions and max pools. And then we have our fully connected layer, which looks like it's a map multiply with a linear add, and then another one, resulting in the output values. So we can look at how the FPGA AI tools are implementing the entire network. And then one thing to add to this, we have, this back up fully, we have an unsupported layers. Oh, there's a new one there. Interesting. I don't remember seeing that last time. Oh, it's because we did the small. Okay, let's run the generic or the medium real quick. Go back to generic, and we're gonna close this, reopen it, preview. Okay, so our slice function is not supported in the FPGA, so it's going to do the slice in the CPU using a crop function, which is really convenient that the FPGA AI core will automatically split these functions between the CPU and the FPGA portion of the DLA implementation. Really useful that way. Did this? Curious. Does this change at all? No, it's the kind of the same structure. Okay. Cool. So we compiled it. We looked at the dot functions. We can see how the FPGA will implement our neural network. So let's go and look at it in more detail. And do an optimized architecture. So for that, we're going to go to the design guided journey, or the AI design guided journey. And we're going to look at compile and generate your FPGA AI IP and look at optimizing architecture. Oh, I'm going to take a quick water break. Okay. If you joined in the last 15 minutes, thank you for participating in this live stream. We're looking at the MNIST example using PyTorch for the Altera FPGA AI tools. This is a sponsored live stream from Altera. Thank you for joining us. If you have questions along the stream, feel free to put stuff in the YouTube, Twitch, chat. LinkedIn is not acting up, or is acting up today, so I don't know anyone participating through LinkedIn how that will go. But we've been able to train the network and compile it down for the DLA core. Now we are going to take a moment to optimize the system. So if we go to optimizing architecture for our FPGA AI core, we can pick the highest performance or optimize for a specific frame rate. So if you follow through the guided tour, you can go to this command and you can pick the max options or the max resource options, talk about utilization max percentages, and pick an architecture as a default. Kind of curious. Input architecture. Maybe we should try doing there's a lot of fun information here. Okay. I already have these commands specified here. So let's go to the max performance. Okay. So this is going to take a little bit of time, and it's going to determine what is the max performance for our system. It's going to be interesting because we got 41 frames per second on the generic. Maybe we should throw the generic in there and see if we can get better performance. I know that the Agilex, it was it. Let's say it can be difficult to try to prototype this without actually having the physical hardware. You can get licenses, whether evaluation licenses or full licenses for the FPGA AI tools, Agilex 5, Agilex 7, maybe ARIA 10, that you can follow along with this workflow. And be able to prototype your kind of pre-optimize models in the OpenVINO zoo, or be able to do your own custom neural networks. So hopefully these examples help you. So we now have a generated arch. So if we go here and change this to generated arch. Oh, okay, I got the 57. That's really good. Okay, let's go up to this tool. And it's actually smaller? No, it's 140,000. That's pretty massive, I think. Right? 6,240. That's using about 2x more than the performance example. When we're doing MNIST, we don't need to do 60 frames per second when it comes to, likely, we don't need to do 60 frames of getting all the different letters. Well, it's 60 frames per megahertz. We don't need 30,000 frames per second potentially for this. So we want to now optimize our network to be as small as possible. So we're going to take this example here. And we're going to try to find the smallest net architecture that supports 100 frames per second, which is should be very easy for the MNIST data set. So we want to see what's the smallest architecture that the tools will optimize for us. And this is going to take a bit of time. While this is running, we definitely have viewers in the chat. Feel free to ask questions, and we can go through some more details on the training, the models, the architectures, and the FPGA implementation. I'll say 123 asks is for the performance architecture, was it less than 150k LUT? Yeah, so the performance architecture here is about 62k ALMs. And I don't want to say LUT because that translation is not the best when you're trying to compare different systems. ALMs include more than just the LUT. So it's important to look at the ALUT, which is 56k, registers, which is what, 2,000 or 200,000. Got the DSPs and the memory units. Well, thank you for the question. While we're waiting, I can talk a little bit about what we hope to do in the next stream, probably 2 to 3 weeks, and that will probably be the last of the Agilex 7 FPGA AI series for the time being. I want to look at more of the advanced YOLO neural networks, YOLO 5, YOLO 8, and potentially YOLO 11, and go through examples of how we get these working on the FPGA AI tools. So hopefully when everyone's interested in trying to get modern, state-of-the-art classification and identification pose neural networks onto an FPGA AI system. If this doesn't change soon, we may have to... Okay, that's good. Probably, yeah, it went really big. That's 300K thousand. Like limit those. What's the limit on these ones? I should have limited the resources. I dropped those all. These are much smaller. So right now it's doing multiple variations with different resources, different ALMs and memory units and DSPs, and trying to evaluate what the frames per second would be for that system. And it keeps getting smaller and smaller, so hopefully it's running faster and faster. Oh, we have a question from Rebecca in the YouTube chat. Now that we have this tool, is there any advantage in designing a network for FPGA from scratch? Okay, so Rebecca, that's a good question. Doing a neural network from scratch on an FPGA is actually, once you start getting into state-of-the-art modern neural networks such as YOLO or LLMs, Llama, ChatGPT or stuff like that, your coefficients dramatically increase. And the problem isn't so much about creating the convolution or creating the max pool or something like that. The layers are, kind of relatively standard FPGA operations. The difficult part is creating the memory architecture, the memory interface to load the data and the coefficients for each layer during operation. And that gets relatively difficult. Using a pre-built structure or infrastructure like the FPGA AI tools provides you that memory structure. It has a dedicated DDR controller to the external DDR memory, and it's able to do the coefficient and data loading within the system really easily. If you wanted to do a neural network from scratch, you would have to do your own memory loading for that. And the skill set between a really good AI developer and someone who's good at doing DDR memory controllers, there's quite a gap in that skill set. So while it's probably great as a learning exercise, it is relatively costly in the implementation part. But Rebecca, thank you for your question. That was a great question. Manos has another question. Are there any Agilex 7 dev boards available at a good price? So a good price is going to be, I would say, a relative phrase. Good price for a student, good price for a hobbyist, good price for a startup versus a more established industry. A lot of times for a more established industry, finding an Agilex dev board and whatnot is well within the price range for them that they can get started in prototyping. For a student and whatnot, the Agilex 7 is targeted more to industries and data centers in such a way that it would probably be out of the price range for a hobbyist and a student. But with the Agilex 5 and the Agilex 3 coming out, and also the Max 10 and Cyclone, if the AI support goes that way as well, are more affordable options to be able to I guess, play around with these tools in a more affordable environment. Oh, looks like it's almost done. There are also probably options to either Intel Altera hosted or third-party hosted data centers that have these FPGAs available. So you could potentially rent an FPGA at a data center for, your a price per minute or something like that. And you can look at that option. It'd be really good to look into that option, but I don't know anything available at the moment. But thank you for your question. So we were able to generate a new core. So we go here. We have a generated architecture. Let's go ahead and look at the size of the generated architecture. This is only 15,000. This is even smaller than our small, right here. Small, soft, max. Okay, so this is 17,000, and our optimized network is 15,000. Let's go ahead and run that. Here we go, run it for the generated architecture. And this will get us close to 8,000 or 7,000 frames per second, which is still great, but we're using 10x less resources, and this might be close to like only 1% of the Agilex 7 FPGA, which would make it a very practical architecture to load into like an Agilex 5. But that's really cool that you can optimize your architecture, reduce the utilization, rebuild the design. We're going to go ahead next and actually run the MNIST on the FPGA. Unfortunately, we don't have the time to rebuild the whole network for this optimized architecture. So we're just going to run with the normal performance default architecture that comes with the SD card binary with this example. Okay, take a drink real quick, a little drink break. Okay, we're probably down to the last 15 minutes of this live stream, so thanks for joining us. If there's anyone who's joined in the last 15 minutes as well, this is a Altera sponsored live stream. We're taking a very basic neural network, the MNIST, and we'll use PyTorch to get the data set, to make the model, to train it, to export it with OpenVINO, and then compile it for the FPGA AI tools for the Agilex 7 FPGA. So now that we have it compiled for the system, we're going to go ahead and run it on the FPGA. And let's go look at the terminal output. I actually probably want to reboot the system. These other examples. Okay, cool. We're gonna go ahead and reboot the system real quick. We're rebooting the FPGA, so we kind of have a clean slate. Let me get my commands ready. Yeah, this is one. Close this, this. Sample images. I think we want to do. That's what we want. We're gonna run the benchmark real quick. Oh, it's not gonna work because of the JPEGs. It's fine. Okay. I think we're good to just run down the system. Okay, we're gonna let me make this bigger so everyone can see. So this is the UART terminal for the SoC. Give it a second. Login as root. Let me to do fonts. Make it what, 20? Okay. Ooh, made this thing way bigger. Okay, so we're going to SSH into the system with this IP address and get going with our more interactive example for the system. this reconnect in a second. There we go. Okay, so first thing, we're going to application folder. We're going to restart the UIO devices. These are basically some GPIO devices that are on the Linux memory map, and these control the DMA, the FPGA AI core, and other things. So we want to enable this or restart them so that our basic driver software can interact with them. And then we want to grab the environmental variable for the root application here. And then we're going to run inference stream. And this is going to run the streaming interface for the MNIST example we just built. Okay. So we have kind of two Python examples to walk through this. The first one, so this is basically a copy of what we've done previously. So there's nothing dramatically new. If you want to learn how this works, look at the previous stream. We're just setting the height and width to 28. This is a really tiny image. We have some example images, just 4. We can look at those. These are the 4 example images that we have going. Are we doing extra large icons, I guess? So we have 2 zeros and a 1 and a 4. Just 4 examples to get going. And then we're going to output the we're going to print the output, and then show which one is the max. Very basic example. Okay, so that's also in the app directory. We're going to use Python 3 to run this interface. So we're going to go MNIST v1, and this is just going to run the 4 images, the 0, 0, 4, and 1, and it prints out the output and gives us the max value. And it's fixed to go slow. I took out the time functions, and this flew super fast. But this is just an example of it working correctly on the FPGA. So our custom neural network works within the FPGA AI core. But this is really boring. I want to do something more interactive, something more visual. So we have version 2. So if you look in the GitHub repository, we have version 2, and this is basically letting us. Oh, did it not get updated? Oh, I gotta fix that. Let's fix that real quick. Grab this. Terminal. Where's the terminal? Is it down here? Okay, we'll do a new terminal, yes. Oh, it's right here. Cool. Get the status. We can check it out. Did that not change? It didn't change. Okay. This is much different than what's here. Okay, cool. I need to learn how to show my terminal again. Okay. Maybe we'll just hit new terminal. Okay, get status. Okay, so we're gonna do git checkout head. I don't need that. I want the MNIST live demo. Go ahead and clear that. Get status. Okay, that's the only thing we need to do. Git add, or no, git commit m. I want to make sure you people can see this. Update for MNIST 2. Okay, so that should be up to date on the repository. So everyone should be able to follow now. Okay, so V2 is basically we're providing a UDP socket to send this data. And that's all V2 is doing. It's doing the exact same thing. We're just able to send data over the UDP Ethernet packets. So in our notebooks here, we have an MNIST draw notebook. And this is using, I'm not sure how to pronounce that, but they're using TK, right? Using TK to create a interactive draw environment, right? So we can draw and we can send it, and we can see that the NumPy is sent over the UDP socket right here. So feel free to look at the code, see how it works. It's relatively simple. Okay, so now let's go here. We're going to run MNIST v2, and let's see. Much. Okay, let's close this. Yeah, let's get this in a size format that everyone see well enough. Okay. Let's put this in the background, I guess. Okay. So we can draw a 0, send it. So here are our 10 values, and the 0 index got 1,000. There, canvas, write a 1. 10. It thought that was a 3. Okay, let's thought that was a 2. There's a 1. Okay. There we go. A 2. That's very good confidence. 3. Good. 4. I went to scientific notation for that. It's so weird. 5. 6. 7. I thought that was a 2. Let's try to be, I don't know, more exact. Let's see. The 7 was 300. Okay. And this one was 1,200. And then we have an 8. And a 9. Okay. There we go. I wonder what the conditions for that. Maybe it's just looking for that. It's probably trained on that a lot better. This one gets you 4. Okay, here's a 2. Don't like that one. 3. Nope. Does not know kanji. Okay. Control plus. Thank you, Kevin. So that's kind of our demo today. This is kind of like an A to Z demo from your basic PyTorch example. Using the Google Colab, you can train it with GPU. Exporting it with OpenVINO with the appropriate input size, and then using the DLA compiler to convert that to the binary that runs on the FPGA core. There's a lot of information. This is quite a wide presentation, but I hope you could follow along, and that if you want to do this yourself, you have the appropriate source code, appropriate examples, and always ask questions. The next time we do a stream in 2 to 3 weeks, I want to look at ultralytics. So, see if I can pull that up real quick. So for next time, I want to focus on YOLO vision that's provided by Ultralytics. And this has a bunch of different models that we can explore, from YOLO v5, YOLO v8, potentially YOLO 11, depending upon me testing and all the different models and trying to get working examples for them. But I hope I can provide a good example set for our last stream using some of the more state-of-the-art models. If you want to ask any questions before end of the stream, I'll stay on for another 5 minutes and see if any questions pops up in the YouTube or Twitch chat. Let me see if LinkedIn has done anything useful. Nope. But thank you for joining us on this live stream in this example. Hopefully it wasn't too chaotic. Hopefully next time we're going to try to be a little bit more specific, narrow the scope a little bit to just getting the YOLO models working and demoing with interactive examples, images, and whatnot. And hopefully that would be interesting and easy to follow. I would also like to thank Altera for sponsoring this again. I know this was kind of a unique opportunity where we explore something new. I am happy for this opportunity and hope to be able to continue this in the future with additional streams. But thank you for joining us. I just saw Rebecca gave a question on YouTube. What is the real Fmax of the architecture? So the real Fmax on the actual system, we can do that. If we go here, we can run the actual. Let me run it real quick. We may have to reboot the system. Kill this, paste. Okay. The actual performance. Okay, so let's talk about this. Let's set this up. So we're running the performance architecture. So this forecasted, 17,000 frames per second. The FPGA, we were able to achieve 7,000 at 37 frames per second. This is 200 megahertz, right? This is estimates. If we did a 500, we do 1600 or no, 16,700 frames per second with a 33 frames per second megahertz. We actually achieve better per megahertz performance on the actual hardware. And here, the forecast value is slightly less than this forecasted value, but it'd be interesting if we could push this to higher clock rate to see what we could achieve. So there is the actual performance. Let me put this window here. Okay. There you go, Rebecca. There's the actual performance. Okay. Answering question on LinkedIn. Monk, you're asking the price for the DE25 Agilex board. Let me see if that's posted. I don't have any information about that price point at the moment, besides what's publicly posted. But we can see what the order now page says. Rebecca, you asked how we could increase the Fmax architecture, or Fmax. So to increase the Fmax, we could either do multiple FPGA AI cores with multiple external DDR banks. Usually the limitation here could be the FPGA AI IP core or the DDR interface. So depending upon that, we could do more FPGA AI instances to try to linearly increase our performance, but it's probably going to be dependent upon our memory. The other thing we can do, like we did before, is we could change out the architectural file, rebuild the FPGA bit stream, so that we have a more optimized architecture for our network. If you remember, which one was it? It's above all this stuff. Okay, right here. So this was the max performance one. This is 57. This is almost like like an 80% increase in frames per second. And this is using a lot more resources, right? Where did we dump it out? This is using 140,000, which is probably about 25% of the Agilex 7 FPGA. So that's one way we could increase the Xmax for this device. Okay. Terra ASIC hasn't posted any pricing on the DE25. I don't have any information to share about that, but I hope that they post that information soon, and I will post about it in my social media feeds when that does happen. So Monk, I look forward to figuring out the price as well. And thank you, Harry, for complimenting the demo. Okay. If that's all the questions for now, I think this is a good place to end the stream. Thank you, Altera, for sponsoring this stream. Feel free to follow, like, subscribe on these various interfaces to see future FPGA live streams covering various different topics. And thank you for being a great audience.